it's working. Can you check really quick? Just to make sure it's working.
I checked a little bit ago.
Okay.
I thought I knew one student that could be here. Maybe you stuck at Atchison.
I tried to sell it. I tried to sell it. Sure. There's a bottle of water right up there for
thank you.
If you guys have cell phones, if you can fill out that pre-questionnaire, there'll be a post-questionnaire at the end too, if you're able to access it. What?
Forms. I wonder how that URL, what's the GLE, that domain, what does that suffix mean? Greenland? No?
Probably gulag.
Gulag. Or some glee club.
Oh, glee club, I like that.
What the hell is a glee club anyway?
Male choir in high school.
Male choir?
Yeah, I think so. Glee club.
You want to start one, Adam?
Maybe they could. I suppose women can have a glee club. Girls glee. Yeah, there was girls. Girls glee and boys glee. It's a unisex course.
I'm going to wait a couple more minutes and then start it. I'm hoping more students will wonder.
I know there was a TV show.
Oh, golf glee. Yeah. That was co-ed though, wasn't it?
Yeah, I guess. I don't know.
Well, I don't know. That's the way it was in our high school. Just listening.
Adam, there's cookies and stuff in the back if you want some.
Yeah, I'm trying to watch my girls' figures. We should get a door or someone look again.
Greg, can you open that door?
Somebody's lost.
What, this one or the outside?
Oh, I just saw someone peeking in. I wasn't sure if they were trying to get in.
Should give like this little smoky sausages and cheddar cheese, like maybe some broccoli.
Mm-hmm. I agree. That would be awesome.
Get the charcuterie tray.
But
crudité.
I'm trying to minimize the money spent. Charcuterie tray?
Yeah,
I don't know. It just seems like it's always sugar.
I know, because that's
cookies and stuff.
the stuff that doesn't require refrigeration.
Cheap empty calories.
What? Yeah.
I'm not sure smoky sausages would require refrigeration.
I don't think so.
There's enough
Salt.
There's enough potassium nitrate in those things to
What can happen?
blow this place up.
Kurt Vonnegut said, what can happen to cheese that hasn't happened to already?
You want to get started?
Okay. Rolling.
Yeah.
So thanks for coming out tonight, everybody. Dr. Joseph Kendall Morwick is an assistant professor of computer science at Missouri Western State University. Joseph grew up in Ohio and earned his PhD at Indiana University, studying artificial intelligence. Since then, Joseph has worked for many small colleges, tech firms, and tech volunteer organizations across the Midwest. His interest in ethics and technology grew from his studies in AI and the impact that emerging technologies can have, and also his desire to help ensure the Midwest region has a prominent seat at the table in technology research and development. So please welcome Dr. Joseph Kendall Morwick.
And also, AI a little today, and in particular algorithmic bias. Let me pull up my slides.
I might have to plug it into the tower down below.
Where's the? Is it in here?
Yeah. Sometimes
Well, this is also this USB key has been giving me some fits.
yeah, sometimes the plug in on top here doesn't work. It should.
There we go.
All right.
Okay, so I titled my talk Machine Learning's Human Problem because really the issues that I'll be talking about don't have so much to do with the machine learning algorithms as they do with the people that are using the machine learning algorithms. And I want to talk to you a little bit about machine learning so that you understand the nuance to that, because it may not be something that you didn't already know, but I feel that really understanding how people are the problem more than the algorithms themselves are, it involves understanding a little bit about how the algorithms actually work. So before I get too far, I want to talk about artificial intelligence in general and give you a kind of a broad picture of how AI affects our lives, or at least how it could potentially affect our lives in negative ways. So a lot of advances in machine learning have helped for applications like self-driving cars and whatnot, but they've also led to other concerns. So now, there are a lot of privacy concerns because cameras can be capable of recognizing people's faces very easily. And in fact, that's at this point fairly old technology. I don't know if you've seen Steve Buscemi as Jennifer Lawrence recently, but this is a new technology called deep fakes. So they took a video of Jennifer Lawrence and a video of Steve Buscemi, just had him move his head a little bit. And if you watch this, Jennifer Lawrence just becomes Steve Buscemi, which means that you could become anyone and anyone could become you in one of these videos. And if you want to fake, a president or whatever saying some awful things and throw it up on TV, you can do that. In fact, the code's available up on the web right now. You could do it tonight if you want. It's not that hard. The one people probably talk a little bit more about is automation, because we've been concerned about automation for a long time. You can see the statue of John Henry over there is what I'm always reminded of when we have this discussion. And although he did beat the machine, it was somewhat of a Pyrrhic victory. And at least, according to the folk tale, he died doing it, so the machine ultimately won more or less. And that's really the concern: is our machines, as AI increases in power, is it centralizing power, right? So can one algorithm held by one person do the same work as 100 people? That means that that one person has more power and it's not distributed as evenly anymore. Drones. So the technology for drones themselves isn't really so much a lot of artificial intelligence, but coupled with some of the other technologies we've been looking at, imagine miniaturized weapons on these. There's a lot of potential things to be concerned about there. And beyond that, who knows what else? There's probably problems that we haven't even considered. Now the funny thing is back when I was starting my, back when I was applying to grad school and told people I wanted to study artificial intelligence, oh, this awkward small field you've probably never heard of, where people do these weird things that most people think are inconsequential, right? Not so much anymore. At this point, I don't need to tell people I'm not making the Terminator, but they might worry that I'm, making the next algorithm that will decide whether they get a job or not, right? So one thing I want to plug is a book by Kathy O'Neill. So as I focus in on the issue of algorithmic bias, which isn't really so much coming up in the other issues I brought up, but This book really focuses on it, has a lot of very good information. Kathy O'Neill's among many people talking about the issue, but I would say probably one of the more foremost speaking on it right now. So I would suggest looking into some of her work, but before we get too deep into that concept, again, I want to come back to just what machine learning is in general. So machine learning was in the title of my talk, not AI, and there's a reason for that. But I do fear that some of these terms just are all buzzwords, really, when we talk about it. So what's machine learning? Well, is it data science, and what's data science, right? And what's artificial intelligence, and data mining, analytics, deep learning, business intelligence, advanced modeling, algorithms. I don't know, did I miss any that some of you might hear thrown about in the same sentence as machine learning that you can think of? The point is that I'm not sure that, for one, there is maybe a lot of overlap among these terms and a little subtlety in between them. Artificial intelligence you could see as more of a blanket around all of them. And in fact, what was more traditionally seen as artificial intelligence wasn't even machine learning at all. In fact, my background isn't so much in machine learning as it is in logical reasoning and that sort of thing in AI, but because machine learning has become such a hot topic, of course, as you know, primarily as a teacher more than a researcher, that's something that I've had to become involved with quite a bit. So, so let's look at what machine learning is, or well, before that, what artificial intelligence is in general. So the way I kind of expanded beyond machine learning, how I like to describe it, is to more so say what it isn't. So we're mostly familiar with what software development is, right? Some programmers got together and wrote Microsoft Word, right? So what do we expect from software development? Well, we expect it to work pretty much all the time. If you open Microsoft Word and you're typing and it crashes, do you say, oh well, it crashes sometimes, it's, you know, we deal with it, it's fine. No, you're pretty angry about it, right? Because it's not supposed to crash. They're supposed to write it bug-free, right? It's supposed to work. Well, that's the difference between artificial intelligence and software engineering. If artificial intelligence works about 96% of the time, it's Miller time, right? We're all celebrating and we're very happy. If Microsoft Word works 96% of the time, it's a disaster. So an example of artificial intelligence might be Clippy, if any of you are old enough to remember Clippy. Clippy would try to figure out what you're doing in the article and make some suggestions as to what it thinks you should do. And it was wrong probably most of the time, but that was, I guess, perhaps Clippy's undoing. But if Clippy was right 96% of the time, Clippy would still be around. So that's artificial intelligence in general. I like to think of it as solving hard problems that no one expects you to get right all the time, but you know that you're doing pretty well if you get them right most of the time. So what's machine learning? Machine learning is a very kind of specific, more a very well-defined view on that kind of problem-solving process, and of course it involves learning to some extent. So how do we model learning? Well, machine learning algorithms learn from data that's available to them. So you have a data set, we call it training data, that you use to provide to the machine learning algorithm. Machine learning algorithm could take many different forms. There's, you know, nearest neighbor, decision trees, neural networks you might have heard of, deep learning algorithms, support vector machines, that sort of thing. But the machine learning algorithm will then generate a model. The model is actually, not the algorithm, the model is actually the thing that's making the decision. So the model itself is data, right? You put data into the machine learning algorithm, it spits you back some other data that models the rest of the data it has not yet seen. So new data that you see goes to the model, and the model makes a decision about that data. So really, when we talk about bias in algorithms, yes, there is bias in algorithms, but we're mostly concerned about bias in the model. We're also, to a certain extent, or a large extent, concerned with bias in the data, but I'll get into where those lines come up shortly. First, I want you to see what a data set looks like that we would work with in machine learning. This is the very well-traveled IRIS data set, and I say that because any first course in artificial intelligence, you'll probably see this very early, or at least the first course in machine learning. What a data set looks like is you've got a bunch of individual data points, and in this case it might be a single flower. And these data points will describe the flower in some way. So we have a series of what are called attributes. And these are just measurements. Someone literally walked up to the flower and measured a few things and wrote that down. Right? So they measured the sepal length, sepal width, petal length, and the petal width of a bunch of irises. And that's what the data set is composed of. That and also the species of iris, which is a little special because this might be the thing we're interested in predicting. Right? We could look at the DNA and figure out exactly what species it is. Or maybe we could just do a few measurements, throw a little machine learning at it, and all of a sudden we know what the species is. Right? So let's see what a model looks like if we were to try to make a judgment like that. So I mentioned well, the decision tree learning algorithm is one machine learning algorithm that will produce a decision tree model. And I picked this because not all of the models are that easy to look at and understand what they're doing, but you can make sense of this one even if you have no idea what it was before I came in here, right? We look at the petal length. If it's less than 1 or greater than 1, we kind of follow the flow chart, right? If we get to a purple block here, we make a decision. So if we have a petal length greater than 1, we'll just say it's a setosa. If it's less than 1, we ask another question. Okay? At this point, we ask what the petal width is. If it's less than 1.5, we'll say it's versicolor. If it's greater than 1.5, we'll say it's virginica. So looking at the example we had in the previous slide, see we've got petal length of 4.7. Which is greater than 1, so we'll say setosa. But in this case, that's a bad guess, right? We've got versicolor, so maybe not a great model there, but models aren't right all the time. So how does the machine learning algorithm generate these models? Well, the training data is actually composed of kind of two parts. We've got raw data, and there may be a pre-processing step. Just so you know, that pre-processing is often called data wrangling and is a topic more important in data science more generally. But basically, we've got a bunch of data that we can use to learn something from, and then we also have the correct output. So this is an example of what's called supervised learning. There are different kinds of machine learning, but I'm mostly focusing on supervised learning. It's mostly what you see. What that means is that you're given data along with the correct answers. It's sort of like if I was teaching a class and I handed out a bunch of exams with the correct answers on them, right? And you use that to study, and then later I give you an exam that you hadn't seen before. Well, maybe you could have looked at the questions and answers before and gleaned something from it, like a practice exam, right? That's how machine learning algorithms work. So once they produce a model, how do we know how well they learned, right? We could just throw some data at it, get a model, and put it to work, but that would be a bad idea if we didn't know how good it was doing at its job, right? So this is how we, how a scientist is going to go about validating the work that a machine learning algorithm is doing. A rule of thumb is that we'll take about 10% of the data as test data, so we'll hide that from the learning algorithm. We'll send the other 90% of the data onto the learning algorithm for it to produce a model. Okay? We'll take that remaining 10% of data, and this can vary, it's not always 90 and 10, but that's kind of a rule of thumb. We'll take the 10% of data we held out, give it to the model, and have it see what spit out the answers, right? We'll take 10% of the correct outputs and then just evaluate, well, was it right or was it not right on those? And the fact that it never saw this 10% of the data means that it's an independent judgment that we're able to observe here. So let's see what the, for the iris data set, what some of the output might end up looking like. This is what's called a confusion matrix. And what we've got here is each of these rows represent when we're predicting virginica or predicting setosa or predicting versicolor, and then the columns are what the actual species was. So you can see when the flower was virginica, 49 out of 50 we predicted as virginica, so that's pretty good, right? We had one mistake, we predicted one of those virginicas to be setosa. So over here you see for the setosas, we had one of them as virginica, and that's the same one. You can see that there's some symmetry on this chart, right? And 47 of them we were right on. And so hopefully down the diagonal you've got some high numbers, right? 2 of them we misclassified as versicolor, and then you see the symmetry also here. So the total, if we have 150 data points, we might want to be looking at accuracy here. If I add up all the correct, everything down the diagonal that I got, divide by 150, I've got about 96% accuracy, which is, I think, actually a little higher. I made up these numbers. It's not an actual experiment I ran, but if I got 96% on there, people would be pretty happy with the iris data set. That's maybe about the max you should expect. Accuracy is, yeah, that's basically your score on the test, right? We're all used to seeing scores like this and doing evaluations like this, whether it's people or whatnot. Machine learning can and almost always should be a little more nuanced than this. Accuracy isn't all you should be looking for, and I'll give you several reasons why that is as we go on. So I'll just give you one real simple one that's just very similar to what we were looking at before. Let's say that we were, and I will talk about a case that was doing this in a moment, using a machine learning algorithm to detect whether whether a patient has a tumor. You've taken an X-ray, you did some image recognition on it, and you're trying to determine if it's a tumor or not. So let's say that the system 150 times when the patient does have cancer says that they have cancer. Great, they can go get their surgery, hopefully they'll be cured, right? And then let's say that we predict that they have cancer 70 times when they don't have cancer. So that's not good. That could be potentially dangerous, right? It might lead to unnecessary surgery, something like that. Certainly want to avoid that. Most patients that'll come in, we could expect maybe don't have cancer, so you're going to see a lot of times where we'll say they don't and they actually don't, right? But now we're going to get over here. So this, what I mentioned up here, this false positive is called a type 1 error. In statistics, you'll see this come up. In other scientific disciplines, you'll see this. And then we've got these type 2 errors, which is the person actually did have cancer, but we said they didn't. And perhaps this is even more dire than if we had said they had cancer when they did not, right? Because now we'll do nothing about it and the cancer will grow. So in this case, my point here is that there may be different consequences depending on what type of error we make. And if we were just looking at accuracy, we could have a system that would lead to much poorer health outcomes than one that would differentiate between the types of errors. So accuracy isn't going to solve all our problems. So where does algorithmic bias start to come into play? Well, some of you might have heard, there's machine learning is racist. And it's true that all algorithms have a bias, but a bias, if you hear that an algorithm's biased, don't necessarily think that that's a bad thing. Bias has a kind of different meaning in machine learning. In fact, most of the time, a bias is a good thing in machine learning. One example of this is what's called inductive bias, or I guess the most important example of this is inductive bias. And what inductive bias means in machine learning is it's essentially the bias, how a learning algorithm adapts its data to data it hasn't seen yet. So an example of inductive bias might be an algorithm that follows this idea of Occam's razor. Right? So some of you might have heard of Occam's razor before, maybe in a philosophy class. The idea of Occam's razor is that if you've got multiple hypotheses, you go with the one that's consistent with the data that you've presented and is also the most simple. Right? You go with the most simple hypothesis that is consistent with the data. So you prefer that over a more complex hypothesis. So imagine I've got a two-dimensional data set, two-dimensional data set. One dimension is sort of the input coming into my machine learning algorithm. Let's say the x value is the input, and I'm trying to predict the y value. Okay? So these little dots I've got here will be the data points. There'll be a pairing of inputs to outputs, right? So consider this green line as a model and this blue line as a model. Which one do you like better? Which one seems like a better model if you were to make predictions?
Green line.
Green line. How many people think green line? How many people think the blue line is doing a better job?
Well,
yeah, see, it's not...
It depends on other factors.
What looks good about the blue line?
It's least squares fit, right?
Yeah, we're hitting all these data points, right? We're hitting all of them. We're 100% accurate. Right? Accuracy is super high. This green line does not have that great of accuracy. But what's good about the green line?
Simple.
Simple, right?
Yeah.
So this was our training data. Now let's throw in some other data that the model learning process did not get to see. Okay, so you have a question?
Yeah, the green line only hit 2 points.
Yeah, it hit 2 points, right? And it's not very accurate on these other points, right? But this was the test data, or sorry, the training data. We didn't give it all the data, right? So one thing is, like, what we're really trying to figure out is, like, what are we really trying to model, right? Like, maybe this is, what's a good example? Maybe this is, X here is how much I ate and Y is how happy I am that day, right? I don't know. So maybe I eat a whole bunch and I'm really happy. But it's going to vary, right? It's not always going to fit a perfect, like, it'll be hard to predict because, like, you know, maybe I, you know, fell over one day and, you know, I was unhappy because of that, but it was unrelated to how much food I ate, right? So maybe this day that happened, and maybe another day I you know, found $5 on the ground, so I was pretty happy, and, you know, it's unrelated again to how much food I ate, right? But so there's some variance, right? There's some variance that doesn't fit a perfect model, and maybe this is the rest of the data we didn't see, right? Like maybe it's all actually going around that green line a little bit, right? Like the green line's pretty simple. And if we instead tailor our model to every single little specific example we saw, we're ignoring the general trend, right? We're failing to generalize a bit. And so, you know, when we talk about bias and we talk about generalization, you know, both of those sound like bad things. In machine learning, they're not always bad things. Where we see negative impact of that is, again, a little more nuanced, well, sometimes it's easy to see, and sometimes it's a little hard to see, right? I'll show you some cases of both. So yeah, where's the bad bias? This is good bias here in this green line, at least in this example. Sometimes it is the wiggly line, sometimes it's the green line, right? But more often it's going to be the green line in a problem like this. So where's the bad bias? So there's a saying in computer science that goes well beyond artificial intelligence called garbage in, garbage out. Okay, the idea that if you have bad data, if you have garbage data, and you put it through some kind of computer process, you get garbage out, right? There's a very similar saying, you are what you eat, right? So you eat the healthy food, you're strong and whatever. You eat the junk food and you're weak and not doing so great. Same thing can be said of machine learning algorithms. You feed it bad data, you get bad models, okay? So if the data represents people's own biases, right? If we're feeding in people's own bias, then we're going to get a model that really accurately represents people's biases. Right? The machine learning is doing its job. It's modeling people's own biases. So sometimes the problem is just in the data. So 2 years ago, I was visiting assistant professor at Central Missouri in Warrensburg, and for the first time, I taught artificial intelligence before that, but for the first time in my life, I was teaching a graduate level course, and I thought, okay, I need to dig into the literature here and get some more examples for them to work with. I found people citing this Boston housing data set a whole bunch, okay? So I thought, okay, I'll grab that data set and have them do some regression on it. Now, I don't know how easy it is, probably not very easy for you to read all this back there, right? I don't know if you happen to see anything that kind of, I didn't see it right away when I was looking at it, but then I noticed it a little later and thought, wow, I can't believe people are using this data set all the time. See an attribute in there that maybe doesn't look so great? So the idea with this data set is they're looking at a bunch of different attributes of data to predict how much a house is going to be worth in Boston. And it's kind of relevant that Boston's involved here with its history too.
The proportion of blacks by town.
Yeah, so the B attribute, right? And in the first time I looked at this data, it was just there as B. I didn't see all the details. And I was a little chagrined in class when someone was asking, what's the B mean? And I look it up, and I get this. Black proportion of population at low to moderate levels of B, and increase in B should have a negative influence on housing value if blacks are regarded as undesirable neighbors by whites. This is from 1970, right? I'd like to say we're doing a better job since then, but this is still out there. It's still being used. There are some that don't take that attribute into account, but this is an example of garbage in, garbage out, right? If you're making decisions based off of race, then you're literally programming bias directly into the models that you're creating. Now, I want to start to split some hairs here. So in this case, it wasn't the algorithm that was racist, right? the people applying the algorithm may or may not be racist. I would say this certainly crosses a line if you decide to include this in the data that you're using. But there are times at which you can include data that has these problems where you might not even realize what you're doing if you don't think about it enough, right? This one is a little more, I'd say, obvious than others, but in this case, the model was certainly racist. It was programmed into it because of, not because of any one specific individual racism. It wasn't that, like someone from the Ku Klux Klan came in here and made the model or something. It was more that the systemic racism was the issue involved here. The reason that, the reason, if you look at the literature on the data set, it was other white residents of Boston were not as eager to buy a house if they were going to live next to black people. And that's what drove the value down in this case. So it was the systemic racism in the society there. Okay. So basically, bias is also going to go a lot further than race. So it's not just an issue of race, it's any kind of majority or status quo is always going to, like, whoever's in the majority is going to win out in a machine learning algorithm because you're looking to get the higher accuracy, right? So the more often you can be correct, the more often you look at like the typical case, the more often you're going to do well. Okay. Another issue is, well, unless you do something about it, right? And so there's a lot of literature on this topic. I'll plug it in, Kathy O'Neill, but a biased data set could be something like, what if we look at historical values of, let's say, remember that if you're going to make a decision on whether or not you give someone a loan, okay, you might look at their history, or the history of other people giving people loans and try to model that, right? So what could go wrong there?
People just gave loans to anybody.
Well, people can make some bad decisions about who they give loans, and you might model that bad behavior, right? But in terms of how could the model that you produce be biased unfairly? How could it treat people unfairly, potentially?
Well, if you're looking at the people who were given loans in the past, then it would probably be predominantly white individuals who were given loans.
So, right, if there was perhaps racism among like the people who were handing out the loans, right, you would just be perpetuating that if you were modeling ill behavior, right? So again, depending on the data that you're looking at, you're basically modeling what used to happen, right?
The economic differences between the past and the present.
Well, I mean, all of that is going to impact, like anything that impacted the old decision is going to remain if you look at the old decisions, right? So, like, all of those factors.
Could you say that, I mean, would you say that anything, say, that's more than 10 years old could potentially have a bias, any data set?
Well, I mean, I would argue that even now, there's still a lot of issues that will work their way in. It's not always as, okay, so I'm bringing this up as the easy one, right? Let's say you've got like a racist or a sexist mortgage lender or something like that, and you're modeling data off of some of those people mixed in, right? That's the easy one. There are much more insidious ways in which some of this can work its way in. So another one is, so the issue here in this one was biased data sets, right? And this issue can also get a lot more insidious, but there are also other ways in which problems can come into play. So failure to control how the algorithm's trained. This is, have any of you heard of Tay from Microsoft? It was a chat bot that they put on the web. You heard about it?
Yeah.
It was designed to learn from people who were tweeting at it, right? And some of the darker corners of the internet got wise to it and started trying to teach it basically terrible things. And it started saying things like that it supports genocide, because people were training it online to say that. And part of the problem here was that there was no control over how it was learning, right? Like we were leaving it up to the internet who gets to teach it, right? It's like if you don't have any control over what someone's learning, they might learn from the wrong people.
Yeah, but with the internet becoming more prevalent, this is going to become an even larger problem.
Well, if we were that careless, I think Microsoft quickly learned a lesson here and cut this off. But it's an important lesson that you can't just kind of open up the all the tasks that you're trying to complete to the internet and have them do it for you, because they might not have the same goals in mind as you do. Another is when you look at the results of a machine learning model, perhaps you have some misplaced authority. So this is by the way, all the examples that I'm doing, like the last one was a little while ago, but all the ones I'm going to be showing you from here on out are like within the last month or so. In fact, on the way here, I was listening to something on the news about a machine learning algorithm making decisions on who gets hired for a job or not. Literally on the way here, there was a study about that coming out, about bias working its way, pretty similar to that 2 slides ago example. But in this case, this was about a week ago. This was on the radio, and it was an article. It wasn't quite as bad as some of the others I was describing, but what happened was it was actually about 20. It's following up on a study from about 20 years ago, where 10 or 20 years ago, a system for automatically finding tumors, like the one I explained in the other example, was being used, and you know, the idea was that, you know, well, the doctors will look at what it says, and the doctors will use their own reasoning too, right? And how could it hurt, right? How could it hurt to have a little bit of feedback from the computer to maybe flag cases that the doctor should look at a little more closely, right? And it turned out that it did hurt. When the computer program said that someone didn't have cancer, people thought, oh, well, this is a machine learning algorithm. It's got to be right, you know, like, or at least maybe they didn't think that directly. But they gave too much weight to the algorithm, and as it turned out, hospitals using that system had worse rates of you know, correcting this illness than hospitals that did not. So it actually hurt. Having the algorithm led to people being less healthy in this case, and they chalked it up to basically people trusting it too much.
They were supposed to be training it.
Right. Well, that's part of it, but part of it was that they were supposed to take it as a cue, not a you know, not the final word.
You'd hope that then the algorithm would look at the fact that it was wrong and try and adapt its method.
Yeah, I think you know, like other means of doing machine learning should be able to adapt better or worse to anomalous situations. That's one place where you'll see things moving a little beyond machine learning as well in other areas of artificial intelligence. But
that data has to be inputted. So who's to say that these hospitals, right?
Well, machine learning, okay, so I won't get too far into this, but...
if it fails to diagnose something, does the doctor have to then input that it was a failed diagnosis? And will the doctor input that information? This
particular system didn't, I believe, have that capability, but there are like what are called online learning systems that can be updated continuously. But even beyond that, this is sort of a limitation of machine learning. Machine learning is great at grabbing the low-hanging fruit, like you know. For instance, when people talk about artificial intelligence, they don't talk about something like what I'm doing here. This takes a lot of intelligence. Like, the back of my head is working really hard to solve a bunch of physics problems, like, you know, in real time, that, you know, you'd sit down on paper and really have to spend some time doing, right? There's a lot more intelligence in bouncing a ball than you would think, or like jumping or whatever. And when we're training robots, have you seen some of the videos of robots like failing miserably to walk or to open doors? Look up robot fail on YouTube when you get home. Yeah. It's very hard. Walking, doing what I'm doing here is very hard. It takes a lot of intelligence. But, you know, when we talk about machine learning, it's sort of the low-hanging fruit. Understanding that this movement leads to, you know, the kind of outcome I want is actually pretty simple. Like, it's easy for us to explain. And machine learning is great at that stuff. It's great at, you know, making those kinds of decisions. It's harder at the higher level reasoning, right? It's not as good at the higher level reasoning. And really, I think there are limitations in what it can do in that regard. So when we talk about, you know, looking at, okay, this is a weird case, what do I do here? That's more of a reasoning kind of thing, right, than a model-based learning activity, I would say. So I don't know that machine learning will ever really do that well in that regard.
So like, it's taking the bad data and constantly inputting it back into its model.
Well, that's certainly a problem. That would be misuse of the algorithm, right? So that would be the fault of the machine learning researcher in that case, right? Like you wouldn't, if you have bad data, you shouldn't feed it back in, right?
Well, I mean, what I mean is if it knows it's bad data.
Oh, sure. Like a negative example. I see what you mean. You know, like you can say this. In this case, you should say that.
So
yeah,
this would be like an iterative learning process.
But that is also absolutely, and that is also another kind of honestly, like being able to work with both positive and negative examples is there's some nuance to that in machine learning algorithms too. It's not very straightforward, but that is something that some will take better advantage of than others. Another issue that came up recently, I don't want to say too much about this paper because it was one I reviewed that I don't know if it'll end up being published or not, but I was reading a paper that was talking about automatically planning routes through a city, okay? And their measure of success was essentially whether they met user preferences very well or not. And so a user could say that they prefer to avoid, crime areas or whatnot, right? So as a measure of success, if they manage to avoid the crime areas and get the user there on time, then the system would work really well. But the issue is we're talking about city planning, right? We're talking about how to make a city better. And there is more to that than simply, making one person, fitting their preferences better. Like, maybe our goal is to lower crime. Maybe our goal is to, raise quality of life, whatnot. But, what would happen if systemically this system came in and, like, this is a picture of St. Joe, just started routing everyone around, whatever crime areas there were as, they were going through the city.
Well,
like there was no more foot traffic through certain parts.
Businesses would decline.
Right, the business would decline, and what would that lead to?
Lead to
more crime,
more poverty and worse crime.
Right. So, like, if your idea is lowering, maybe for that one individual, if your idea is to help them out, you might do all right. But if your idea is to lower crime, this might make it worse, right? And this is again nuanced. I'm not saying that that's necessarily what would happen, but I saw zero. That wasn't the problem with the paper in my regard. The problem for me was that there was zero attention to that. They were laser focused on that issue of accuracy and not thinking of systemic effects at all. And that's the sort of thing that you see, happening all the time in machine learning research, and why we see some of these negative outcomes. I believe. Another one is, so those were how do machine learning algorithms perpetuate bias, unfair bias, where the machine learning algorithms are unfair to some people and not others, right? How do they actually create bias, right? In some cases, they'll create bias where there was none before. So this, again, is from like the last few weeks. There was a case with, actually I have one of these systems in my car myself, not one of the ones studied, I don't think, but a similar system that would detect pedestrians and stop if there's a pedestrian in the way of the car. And the paper that I'm referencing down here did independently checked based on race, so the race of the person that the system is trying to detect, and it was 5% less accurate depending on skin tone. So it literally didn't see some people depending on their race as people. And this is a bias, yeah, literally. So this was literally a racist algorithm. And it creates inequality where there was perhaps none before. So it's something that's even introducing new problems, right? Not just perpetuating biases people have, but actually making new ones. So those are the problems. And, I paint a pretty dismal picture of AI, I guess, but really, what can we do to combat this kind of problem? Because really, AI can do a lot of good. Imagine, I've talked about concentrating power in a small place, right? Well, on the other hand, part of the importance of AI is you can take that power and just multiply it. You can scale it up as high as you want. Imagine that everyone, what if that medical diagnosis program worked really well, and you could have it in areas where you can't send a doctor, right? You could really put people on a more level playing field with AI, and I want everyone to think about, not just what are the problems in AI, but how can we do it right so that it can really help people, right? And in this case, you really need to consider all the different biases involved. You can't just go in and look at your accuracy line and expect to get something good out of it. You need proper controls over data collection. So you need important selection criteria. Like the housing data set that I showed you absolutely should not have had that attribute in it. It shouldn't be perpetuating that kind of judgment. It should be based on something that's fair, right? Something that would fairly, so that no matter who you are, when you come in, you would be judged on your merits, not on the color of your skin, right? It should take into account diversity. One of the issues in that car study, or not study, yeah, the study on the cars, is that they found that part of the reason it didn't recognize people with darker skin tones, any of you have an idea why it failed? Relates to diversity.
All the programmers are white?
Close, very close. It wasn't the programmers. I mean, they may have been, but that wasn't the issue as much.
Maybe it was the socioeconomics of the area. Maybe it was.
It could have been a little bit, but that's indirect.
Was everybody they tested it on?
Everyone they tested on was white, right? Or not everyone, but they had a very disproportionate bias towards white people in the study, right? And so that did two things. One, the machine learning algorithm is already trying to go for the normal case, not, and so if it's seeing a bunch of white people, then that's what it's focusing on, right? It's not looking outside of that very much. The other thing is that, so part of it's on the algorithm too, like the algorithm might not be taking into account, like if you're in an area where people are like 50% white, right, or more, then any other case would be seen as anomalous, right? And the machine learning algorithm needs to be selected also so that it takes all cases into account equally. You could even build more than one model, right? You use it on different kinds of people and build multiple models and use them all in parallel. But they didn't take that into account. So diversity in your training, right? Like, this is called the class imbalance problem. If you have, more of one than another, but you expect to serve both, you need to have them be equal. So you need diversity in the data that you train with. And another is access, how you control access to the learning environment. So you need to make sure that the right people are putting data in, that people are trained, they know what they're doing, they're not just random people on the internet, as in Microsoft's case, but even beyond that, like you're not just throwing it to the grad students necessarily, but someone who really knows what they're doing is designing this, right?
It's almost over.
Another thing is that you need to have a deep analysis of the impact of the technology. So I mentioned that context really matters when you're analyzing success. I would really like to see papers look not just at a narrow view of what success for their algorithm means, because you might try a few experiments and then the one that you settle on is the one where you have the highest success rate, right? Well, you're kind of selecting. You need to have your goal in mind when you go into the experiment, not so much when you come out, right? Like you need to think about what success looks like on a broader scale. You need to be mindful of the motivations for success of the project. So beyond that, like, why is it that, is there a reason you want to get a certain outcome? Is there a bias basically injected into the process outside of the experiment, right? And this is just classic, mindfulness about scientific research. It's not anything new to machine learning. But you prefer a publicly funded study to a privately funded one, right? That sort of thing. And also just listen to adversaries. So I think what a lot of these projects could benefit from more is just taking more critical feedback into account, right? And considering, I think people, especially in technology, get very wed to, and I'm not saying that I'm not guilty of this either, get very wed to their projects and stop listening maybe to some of the criticisms about how it won't work in certain environments. And you'll hear that all the time from tech execs testifying on Congress or whatnot about how great their product is and how it couldn't possibly hurt anyone. Like you need to start thinking maybe there is a point that people are making that you need to take into account, right? So that's how researchers can combat it. But whether or not you're a machine learning researcher, I think you have some a stake in this as well. And what can you do? So part of it is just being informed. I do want people to understand this at a more than just a very high level and learn about machine learning and see how it works and demand transparency on how they develop their models, right? So if you understand a little bit more about machine learning, then you can take a look at a more transparent approach to doing it and say, hey, you shouldn't be including this, or you should be diversifying your input a little more, that sort of thing. Support those who are investigating consequences of technology. So, there are investigative journalists and researchers that are trying to help the public, and I think that, the public can help them help themselves, right? And then finally, vote with your time or resources, and I didn't say dollar, right? You might be used to hearing vote with your dollar, but really in the world of tech, it's not always your dollar that you're paying with, right? They say you are the product, and when we're talking about social media, in a sense, that they advertise to you, and that's how they make their money. So if you want them to listen to you, you basically need to say, okay, I'm willing to move to off the cloud and move to something I have a little more control over, and maybe then they'll start listening to you when it affects their bottom line. So that's that's all I have on the topic, but if you have more questions, feel free to ask, and thank you for your attention.
So, my name is Rajam Sal. I'm a math instructor here.
Okay, yeah.
I have two questions for you.
Sure.
It's actually one question, two part.
Okay.
My first question is, what is the difference between software engineering and the artificial intelligence? Do they intersect at some point? Or
Certainly.
Common ground between them?
Yeah, it's a good point. I shouldn't, I guess, have characterized it as such a hard divide, right? But it is kind of a fuzzy line too. Like I remember when I was, when I took my first artificial intelligence class, my instructor was defining artificial intelligence to me, and he said that it's basically a line that keeps moving backwards, right? So this was around the time where Deep Blue was playing Gary Kasparov in chess. It wasn't long after Deep Blue played Gary Kasparov in chess. If you're not familiar, IBM developed a machine, Deep Blue, that ran an algorithm that basically went over, every move you could make in chess. If you're playing someone in chess, you think, well, what if they move here? Then what if I move here, right? And you go down a tree of moves, right? Well, this algorithm would kind of snake through all the possible moves that it could think of up to a certain point, right? Maybe 13 moves deep or something like that, which is where it got its name. And that apparently was good enough to beat a grandmaster in chess, right? So that became huge news. So before that, chess was seen as like the ultimate goal for artificial intelligence. What if we could make a machine that could play chess, Then it would be really smart, right? And now we see it as dumb. Like now we see it as maybe software development, right? Like, oh, you wrote a chess playing algorithm, who cares, right? It's been a while since a grandmaster could beat a computer in chess, right? So, so in that case, what was artificial intelligence moved backwards a little bit, right? It's hard to draw a really clear line, I would say, between the two. I would say that there's no hard definition, but I really feel that something falls a little bit more into the lines of artificial intelligence if you can't expect a very high level of success from it all the time, right? I mean, nothing's 100%, right? Everything's going to crash sometimes. But if when it crashes, it's truly a mistake and not like acceptable losses, then I would categorize it more as software engineering. I don't know if that answers your question, but.
I've actually coming to this point. Nowadays, we've been hearing a lot about the Boeing 737 program. We have seen a couple of crashes already around the world.
Okay, good point.
So, so because they use the software, also they use the sensor to automatically start some program. So how do you classify this problem?
That's a good question. That's
problem with artificial engineering or problem with software engineering?
Yeah, that's a very good question. I would say what happened there was more of an engineering problem, just because beyond, like whether or not, let's say we've got a sensor that's going to tilt the plane up, and it's maybe 80 or 90% accurate. Well, obviously that's not acceptable, right? What needs to be around that is a lot of a very well-prescribed set of actions that need to be followed, that need to be double-checked, triple-checked, right?
Could be false positive. There could be false positive.
Yeah. So basically, that was one component of a system that failed, right? Like a lot of things that would have to go wrong for it to end up on the ground.
So, and
I would say that because the system failed, I would certainly call that not just a software engineering problem, but just an engineering problem generally. In terms of whether or not it's detecting whether the pitch is going up or down, or whatever led to that sensor failure, that's a good question. It's probably more of an AI thing, even though we don't expect it to be wrong.
That's what I'm thinking. It could be another potential problem with artificial engineering, because even though one person's false positive, false negative could be fair.
Yeah. I guess I'll also say I would need to know a little bit more about it for me to really give a judgment, because if it's just a simple matter of just knowing what the plane's pitch is over 80, we do this, or like if it's a rule that simple, I wouldn't really call it artificial intelligence. But if it's taking into account a lot of different data, doing some kind of modeling on it, then I would probably call it artificial intelligence, regardless of the false positive rate, or false or true positive, false positive rates. Yes.
Well, I have kind of an off-kilter question, maybe.
Sure.
You were saying that 96% success rate is really good. Is that the rate?
So these are all rules of thumb, right? Like I mean, like for a plane, we want 99.99%, right? Yeah. All right. So here's another one. AI is really big in predicting the stock market, right? What would be a good success rate there if you're predicting a stock to go up or not. Like 50.001% would be pretty great, right? You know, so it's relative, right? It's relative to the problem.
I was also wondering that given like a particular data set, maybe its size or anything like that, if there was possibly a way of calculating a theoretical maximum that it could be.
Yeah, there's a lot of that sort of thing. So there's something called the theory of learning that does exactly that. Basically, you look at what is the best possible you can do in this scenario, right? Given the amount of data that you have, like how accurate can you realistically be? So there's a method called pack learning where you can do that analysis. It's really cool. That's one way that, as an artificial intelligence researcher, you can create a baseline for what kind of expectation you can have, because you never expect 100%. So yes, absolutely, that's out there, that's used. We often don't go that far in producing a baseline. Like normally we produce baselines by things like maybe a lower one from like random guessing. Like how well would I do if I was just guessing without putting any knowledge in it? Or you might have an upper baseline that was, I don't know, some other measure of ideal performance, right? And then that's not 100%. And then you try to look at how far in between you go. So yeah, the analysis of machine learning algorithms is definitely a lot more nuanced than what I give you. It's not just that people like are completely ignoring the nuance of analyzing it, but sometimes they ignore the nuance that comes into analyzing kind of the human element of it that might cloud the data and introduce human bias into it.
I had one of my best friends is I teach chemistry here, so one of my best friends is a mathematician, and he develops like the fundamental algorithms for online gambling company. So he develops this he explained it here, but it's like the programs for slot machines and things like this, and he was explaining to me this thing called iterative learning that some of these programs are starting to do, where they took two programs and they started communicating with each other, and through this iterative learning process, they actually kind of developed their own language to communicate with each other. The original programmers could no longer figure out what they were saying to each other, so they shut it down.
Keep going. I'm just bringing up something else.
Do you think something like that can potentially spiral out of control? I mean,
yeah. I can't remember where I had it, but I was talking a bit about transparency, right? So you mentioned that the machine learning researchers don't really know what's going on at that point anymore, and one issue with some machine. Okay, so the two models I showed you, I chose intentionally because they're fairly transparent models. Like you see, like I had a regression model there, right? And you can kind of see that line represents how you model the data, right? I gave you also a decision tree model, and it's very easy to follow, and you understand what it's doing. A neural network, if you have seen one, you'll know that it's almost meaningless. Like you look at it, it's just a bunch of gobbledygook, right? And yet it's one of the more popular ways of working with data at this point. But one of its faults is that you can't really give the model to someone and say, well, this is why I denied your loan, right? Look at this neural network, right? It doesn't make any sense. And that's a fault, I would say, in that algorithm. It's one that makes it a little less desirable. If I came up with a decision tree, and there was a line in the decision tree that says, woman, yes, no, and if yes, then don't give the loan, then you can see like what the problem was right away, right? But in a neural network, that can all be hidden underneath layers of numbers and things that you can't decipher. So I think, yes, you as a machine learning researcher, you should opt for more transparent models when you can.
I'm interested in literature. I got interested in the Shakespeare authorship question at one point. There's somebody, I think Brown University or someplace like that, that's using, that's where I first ran across the term neural networks. They're using this to determine the kind of elements of writing style, like the tendency to use a T and an S in a certain relationship in sentences, or to certain kinds of syntaxes and things like that. And coming up with predictors, taking pieces of text and throwing it in and say, Marley write it or did Shakespeare write it? And think that they use that. I don't think they're particularly literary people.
Yeah, I mean, it sounds like
as a,
maybe like a naive Bayes bag of words model, perhaps they threw at it. Or
yeah, I think they were just using it to see if they could get some networks to work.
Mm-hmm.
What do you mean by a neural network?
So wait, you said they specifically use a neural network in that case?
Well, he did. One of the titles said something like neural networks and something.
I mean, I've seen like a lot of statistical models used in analyzing text. I know that I haven't looked. I don't do a lot of NLP, natural language processing, or at least not on the machine learning side. I have done more on the logic side, but there's a lot of. I think there's a lot of potential for using machine learning to. I mean, one thing that's interesting about machine learning is that it can uncover. Hopefully, you uncover something interesting that you weren't able to really see yourself, right? Like when I say, what we're mostly doing is this low-hanging, simple thing, low-hanging fruit. On the other hand, computers are great at being able to do a fairly simple, mundane task like very, very, very fast and very frequently, right? So you could do an analysis of text that a person could never do by hand and see some interesting kind of relationships. And I think that it's kind of an area, well, we're seeing more and more work in that area, but it's one where there's, I think, a lot of opportunities still. Yeah. I don't know if I'm answering your question. Or,
well, kind of. I'm just, you were talking about, the pen, the...
Yeah, right, yeah.
At that. Mm-hmm. But I have this feeling sometimes that what a machine's doing is, I think a person reading Shakespeare is doing something more like you were talking about that takes
higher level reasoning.
Real subtle understanding.
So I definitely agree. On the other hand, perhaps you can't imagine all the works of Shakespeare's all at once and look for some really simple, mundane thing that only comes from like looking at every sentence, like one after another, looking for the simple thing.
And it's important that it be something that you wouldn't have the time as a professional writer to make this decision on every sentence.
Exactly. Yeah.
It's got to be automatic.
So for machine learning, like we're mostly, and this is again like the whole idea of power consolidation is we're looking at time saving. So whether we're saving time, and this also gets into a bit of the nastiness of the problem with bias in these algorithms. Is if you could save the time of a bunch of humans making a decision, have an algorithm do it instead, the algorithm might not be making quite as good at decisions as people, but it's a lot cheaper. So we'll go that route. And yes, I think like people. We don't really have artificial intelligence that does a better job than the smartest people on anything, right? But it might do it faster. So, like, it might be able to go through, like, it might be like your life's dissertation to go through all these Shakespeare works and look for this simple thing, right? But a machine learning algorithm might be able to do it really fast. But it's never going to be able, well, it's going to be much more difficult for it to do something very nuanced and very high level, right? Yes?
All right. My question.
Mm-hmm.
I've always had this thought regarding artificial intelligence.
Mm-hmm.
I'm not aware of how well it can be done now, but in terms of contextualizing, for example, human emotion, do you think it will be capable in the future for machines to read it?
I think it's an interesting question. I feel like in some ways emotions might not be that hard, No, really. Like I feel like
the response.
Yeah, it's actually a little. I mean, with some people it's hard to predict how they'll react to something, right? But you can there's again a lot of low-hanging fruit. You go kick someone in the shin, you kind of know how they're going to react, right? Like a machine learning algorithm can pick up on that stuff. So a machine learning algorithm might even be able to pick up on like your mood based on some other little things that it's perceiving, right? So that means that a machine learning algorithm could also like model that. Like if you had a robot and you go up and kick the robot, it'll get mad, or like you could develop a model to do that. Now, the question I think you might really be asking is what's going on underneath, right? Like, is it just mimicking what should look human, or is there something more like? Yeah.
Conscience.
Mm-hmm. Right. So, what I would refer you to is kind of a classic thing in artificial intelligence, really the birth of artificial intelligence, is Alan Turing's imitation game experiment. And I used to bring up Alan Turing to my students, and no one would know who Alan Turing is, but now usually about half of them raise their hand. Like, how many of you have heard of Alan Turing? We've got a lot of instructors here too, but so Alan Turing is credited with basically coming up with artificial intelligence, and his definition of intelligence was you put a computer in one room and a person in another room, right? And you pass some notes back and forth. And if you can't tell which is the person and which is the computer, then it's intelligent. Basically what he's saying is it doesn't matter what's on the inside, it only matters what's on the outside, which is maybe not a very satisfying answer to your question, but a lot of people would debate him on that. So, yes.
I kind of think there might be something there, though, what you're just saying, because actually if the robot, or I mean if the artificial intelligence gets a certain stimulus and it motivates beyond their response, automatic response, is to do a certain thing. What's the difference? I mean, actually,
that was his
how
point,
much divorced from mechanics and chemistry is our emotion? I mean,
right? Yeah, and that was basically his point. I mean, he had a very mechanical view of people, I guess, in a way.
Yeah.
But and again, there's people will. This is a big debate in philosophy, right?
Yeah.
So people will challenge. Even at his time, people challenged him on that. And Searle, there's a philosopher by the name of Searle who's kind of the biggest critic of Turing's idea on that, and he had this idea of what if you had like a book that was sort of arbitrarily large with every possible English sentence in it, right? And your response to that. And you had a person in a box who would just go through that book, and someone, maybe they don't speak English at all. They have no idea what the words are, right? But someone gives them a note, and they look it up in the book until they find it, and then they give the response back. And it would pass the Turing test, right? Because it would seem human. But the person in there would have no idea what was going on, and the book would have no idea what's going on. It's just a book, right? So where's the intelligence? Is the question, right?
So if you leave the person in there long enough, reading the same words over and over and over again, I would say that it might learn.
Sure. So maybe a person's a bad idea in there. Maybe we have a really, really well-trained dog, or I don't know. There's proponents of dog cognition, so maybe we just have some kind of lookup table, right? Like you type it in on
I think the point I'm trying to make. I think the point I'm trying to make is that maybe the computer could learn, given enough time.
Well, yeah. I mean, I'm not. I'm probably more on Turing's side than Searle's, to be honest.
Well, yeah, but it sounds like that. Can it make a hypothesis? Can it make a membrane?
Yeah. And so that's the. Well, I'll get your question first, and I'll continue on that. Yeah.
All right. So this is the basic school, science. With that being said, the question is: do you think that artificial intelligence should be more specific, focus on specific things, or should it pull together data from different aspects?
So I think I'm much less afraid of Skynet than I am of people. So if you read, for instance, more Asimov for sci-fi, it's a little, I guess, friendlier to the AI. I think the idea that if we look for general intelligence, that it will suddenly become like decide that we're unworthy and get rid of us. I'm less afraid of something like that. Like I'm all for going for the higher level thinking and looking at that kind of stuff. I'm not that afraid of it. I'm more afraid of what people would do with it. So I brought up the drones before, right? Honestly, that's something that keeps me up at night. What if someone decides that they have a machine learning algorithm that finds all the people they don't like and sends out a drone and it goes around and shoots poison at them?
They've already.
We're not far from that.
I've seen where they've already developed that. Yeah. They develop these little drones.
That terrifies me.
That can do facial recognition, and then they zoom right in and implant an explosive.
So, and now imagine we're already there, right? We already have that technology.
Swarming a city.
They use it military. Military, they use it.
Yeah. We already have that technology. Now imagine a little higher level thinking. What if it was really good at it? What if it was smart? What if it knew if you were hiding behind a rock? What if it, what if it could figure things like that out? Then we're looking at the Terminator. And when we're talking about the Terminator, I'm not so afraid of the machine's mind, I'm afraid of other people. Right? I'm afraid of other people making it do that stuff. I think the machine would be more fair, to be honest.
I don't think the machine would care.
Yeah, I'm glad you asked that because it's very relevant. I'm much more like afraid of the human bias going into the process than I am of anything that would naturally come out of the machine, right? Like the machine learning in this case amplifies people's problems, right? It makes people's own kind of nastiness more of a, so the Kathleen O'Neill book that I mentioned calls it Weapons of Math Destruction, because it's weapons people yield to do more damage, right? Or wield. So, yeah.
Well, that'll help me sleep.
Sorry. Yeah.
What do you English people think of Grammarly?
I hate it.
It's really clunky.
Well, and this gets back to what we were talking about that I was going to get to is I like to talk about the 90, I use this all over the place, not just in artificial intelligence, the whole 90%, 10%, like you're doing over 90%, you're doing pretty well. It's because 90% of problems are usually pretty easy, right? And so when we're looking at like whether it's, I have a friend who teaches French at Missouri Western also, and she has a concern where students will write something in English, pass it through Google Translate, and turn it in, right? Yeah. Well, Google Translate, it's getting better. It's above 90. It used to be around 90%, right? Now it's maybe 94 or something like that. But the 90% is easy. We've been able to do 90% of machine translation for a long time. But every now and then it says like something just completely crazy and weird that you wouldn't expect, right? That's the last 10%. That's the hard part. That really requires higher level thinking. Like a lot of language is very mechanical, and then like really like, or at least translation is pretty mechanical. Like what's the word for food? It's or to eat is or comida, right, in Spanish. Like one-for-one translation is not too hard. It's a lot of words, but getting the nuance of it, that's really hard, right? And well, it's still going to be a long time before machines are as good at people as translating, getting that last bit of nuance, even though they are pretty almost scarily good at this point. Yes?
So you basically kind of answered this question still. I think it was last year.
Mm-hmm.
If you remember the controversy between Elon Musk and Mark Zuckerberg.
Mm-hmm. But Elon Musk and who, sorry?
Mark Zuckerberg, Facebook.
Zuckerberg.
Facebook guy.
Actually, I'm not sure that I do.
Well, Elon Musk was basically advocating, he was basically saying that we should be aware of artificial intelligence. We should try to.
Right, he's very, yeah, it's kind of like me, he's big on strong AI.
And Mark, on the other hand, was saying that you should just let it be free. So, what is your
I think I am a big proponent of, I got into AI, I was very interested in it because I was like, oh my gosh, like, I'm used to, really what got me into computers in the first place was I can have a computer do all the boring work for me. Like I was not the best at math when I was a student in high school. I wasn't very good at math because just the way I think, I would make little mistakes as I went, right? And it always frustrated me and I thought, oh, I'm bad at math, so whatever. I loved programming though, because I could make the computer do that for me, right? Like the computer could do the math and I wouldn't have to worry about it. And I like programming, right? I know. I got a math degree eventually. But, yeah. My undergraduate degree is in math. So,
he did a good math background.
Right, no, yeah. But the thing is like, I didn't realize at the time, but math was more than just calculation, right? And it turned out, I still get laughed at when I'm at a restaurant and I'm calculating the tip and screw something up and they're like, oh, PhD in computer science. But yeah, I'm not the best calculator. I'm not the best computer, that's why I program them, right? And that was my perspective going into college, and I started to think, wow, there's so much we can use computers to do that to help people. Like we can have programs replace kind of faulty human processes and make things more efficient and make people better off, right? And I started getting really interested in artificial intelligence, particularly the medical side of it. I didn't end up going too far into medicine when I got into grad school, but that was probably my biggest impetus for starting that study. And I thought, okay, we're going to make computers that can diagnose diseases, and then people, no matter how much money they have, can go in and get well, right? And then I started seeing like, oh my gosh, like this is ending up doing more damage than it's doing good in a lot of places, right? It's like people are taking it, instead of using it to make other people better off, they're using it to make themselves better off, right? So if you can have one computer do the work of 10 employees, you just fire the employees, have the computer do it, you just saved a bunch of money, right? If you're already pretty powerful, right? And are in the position to take advantage of that. And then that kind of started getting me pretty distressed about it, you know? But I'm not a cynical guy. I think that AI can really do a lot of good, but it's just, it's like anything else. It needs to be regulated, you know? Like, you need to be smart about it. You need to think about it, and people need to hold you accountable if you're in a position to use that power. So I think AI can do a lot of good. I'm all for research, especially kind of mindful research, you know, taking all these things into account. I think if people do it right, we'll solve more problems than we'll create. But I think it's certainly capable of doing a lot of damage.
All right, last question.
Sure, that's fine. Yeah.
I am of the mindset that moving forward, visual data will be quite important in developing artificial intelligence. Am I correct on that thinking?
A visual leader?
Visual data.
Oh, visual data. Okay, yeah.
Because when they started out with artificial intelligence, it was just raw data being collected.
Yeah.
And numbers and whatever else they use.
Right.
But I'm thinking that if it really wants to advance to a certain level, because you're talking about improving them, these are not computational,
Yeah.
But in doing that, the visual process is very important. So in general, visual data is going to be important.
Yeah, certainly. But there's many layers to data, right? So a lot of data science is taking raw data or whatever and processing it in some way, sometimes even processing it with artificial intelligence, right? And then you get different data, and you can do something with it. Like, if you were to look at, let's say, visual data of, like, just this part of the wall, right? What it looks like on the computer is a bunch of triplets, right? Like, you've got a dot here, and it's white, so it's going to be a lot of red, a lot of green, and a lot of blue, right? You're going to have very high values there. And then this is going to be darker, so you're going to see a lot of blue here, but not much red and green, right? And that's what the data looks like raw. So what we can do is some pre-processing on that to do like edge detection, and we can find that there's like a line from here to here, and that's like a whole kind of process. Not really AI, but kind of a mathematical process. And then you get some lines out of that. Well, what do you do with the line data? I have a line from point maybe 50-50 to point 150, right? Well, if I have a bunch of lines, what can I do with that? Well, a whole different algorithm will handle those lines, right? And there's a whole pipeline of algorithms to handling visual data like that that do different things with the data at different stages, right? But it's funny because the best advances for like facial recognition and all that throw away that whole pipeline, and well, at least they kind of streamline the pipeline. If you've heard the term deep learning, and what that is taking neural networks and basically throwing that whole pipeline into a neural network. And again, it's not a very it's not a model that you can really crack and see how it's working that well. A little better than other neural networks, but you just train it on it. There's no other part of the process really, and it can recognize faces. And the funny thing is, the inspiration for those kinds of neural networks for deep learning in that regard is taken from studying the visual cortex in the brain. So they look at structures in the visual cortex, and that's what pushed a lot of research in that. And actually, the people who, a lot of the people involved in that just won the Turing Award. And again, Alan Turing's name comes up, right? Because that's computer science's Fields Medal or Nobel Prize, right? And so the people who were involved with that just like as of weeks ago won the Turing Award. It's definitely a very important area. A lot of good, and again, a lot of bad can come out of that, right?
Auditory data is a little harder to parse, it seems like. Because we need
Yeah.
We infer.
They're both hard.
Well, I suppose they are.
Yeah.
But I mean, if you're looking at the brain network and looking at a certain cortex of the brain,
Yeah.
Seems like, oh, I don't know. I don't know about brains. So.
I don't know a lot about brains either, but
It's just, you know, I mean, when you see something written, you know, you process it differently than somebody
that's true.
reads it.
Yeah, even how you reason about it is a little different, right?
You know, when I was in college, you know, the classes where you're taking notes and then there was one history class or something where the guy just walked around on stage and talked, and you just had to like, you had to process it through your ears, and then translate it into
That probably retained more of that one.
So I'm not a psychologist by any stretch, but on Saturday I was at the conference that I mentioned to you earlier, and I attended a panel on cognitive learning theory, and they were saying that exact thing. They were talking about and how we as instructors can utilize this, how students will process what they hear differently from what they see, and different cues can be more effective in different contexts, and they had a bunch of examples of that. And, I think another thing that really interests me about artificial intelligence, and I think in some of the ways that even myself, I was, not quite, I didn't always think the same way as other people, right? So it would always interest me, well, how do machines think differently from people too? Like, how are they not the norm? And that's one way in which machines would be very different from people, right? Like the fact that our brains are designed around or at least evolved to work that way, right? A machine doesn't necessarily have to.
It's just piped in instead of...
Right, like a machine in a way doesn't have to deal with that kind of artifact of evolution, right? So it's another thing about AI that really interests me is just like a different take on intelligence, right? Like, because intelligence is a hard thing to define.
Right.
And even among people it varies a lot, but like a machine you can look at it as in a model of something completely different from how we think, and yet still intelligent.
Right, and what makes a person intelligent? I mean, we're merely acting on instinct, right? I mean, we can think about all this wonderful stuff, but if we don't have any food, so I'm really thinking about something different.
Yeah, and a lot of studies of animal cognition really interest me too, and particularly like these studies that show dogs are very smart, but then what animal was? I guess like monkeys. Some monkeys weren't, like in certain contexts. But what it turned out was that the dogs are get high reward from doing what the person wants, right? And they really want to please the person, and the monkeys didn't care, right? So like it wasn't so much that the monkeys weren't intelligent; they just didn't care. Like they weren't trying to please the researchers, right? So. It's funny how like we perceive intelligence differently. We're biased in a sense, in how we perceive intelligence because of being human, right?
I mean, like power hungry people, or whatever. That's what drives them, or whatever. I mean, the machine could probably care less. They're not, why would what would give them the desire to want to take over?
Yeah, I mean when we get back to the Skynet and all that, right? It's
that's a human thing. That's not a...
Yeah, I don't trust a bare I trust a bare algorithm fine. I don't trust an algorithm that's been injected with like other people's desires, like,
well, I mean
or
they have no concept of self-preservation whatsoever.
Right.
They could just like whatever wants to.
Wouldn't that does that matter to some extent on how the algorithms are optimized? Because aren't like the machine learning aren't they basically kind of like a reward system, kind of insofar as you're trying to optimize something. So if it's geared toward optimizing this particular thing, then maybe
there are different.
That would have to be given to it again.
There are different approaches to machine learning than what I was like. I was trying to give a very simple model just to get the idea across, but supervised learning is not the only way to go about machine learning, and one other way is called semi-supervised or reinforcement learning, where instead of giving them the correct answer, you see what the output is and you say, or, right, like you just say it did a good job or not, or maybe you give it some like reward that could vary in how intensity or in intensity or something like that, right? Like reward for it would just be like, it depends. The algorithm would say like, if it's a high reward, I will try to exploit this data more. If it's a low reward, I will toss it and look at something else, right? So it's all in how the algorithm works.
But you'd be your subjective judgment on is training the thing.
Yes. Yeah. So a machine learning algorithm, so a reinforcement learning algorithm, will take your subjective judgment and the feedback that way, and try to incorporate it in understanding the data. That's how it's programmed to work, right? So you provide the sort of smarts, and it's like what we've seen are supervised. It's remembering the answers more, but in this case, it has to find the answers on its own. Yes.
I swear this is about.
That's fine. My car's. I need to probably wait a little while for my car to charge anyway. So.
All right. We know that artificial intelligence is called data, and we could try our best to try to teach it to learn empathy or whatever, or learn conscience. Now, on the other hand, I started thinking about this in last year and the year before. We're in the future, where technology catches up, where we can map the human mind on a chip, and by that point we'll be able to overcome the limitations of human being. We forget things, don't think fast anymore, and stuff like that. Let me just pause that there because I asked another question.
Okay.
My question is, what do you think of that?
I'm afraid of that too. Have you heard of the singularity?
Yeah.
Ray Kurzweil. It's funny, I have a friend who I went to high school with actually, who works at Google now. And he was at a meeting in Google and like sat down and he looks and there's some guy next to him, he's like, whatever, and he like looks at his name tag and like, oh, that's Ray Kurzweil, like sitting right next to me. He's like, that's what happens at Google, you sit next to Ray Kurzweil, right? But Ray Kurzweil's famous for, well, for one, for keyboards, if you've ever had a Kurzweil keyboard, right? But also for the idea of the singularity, where there's a point at which the evolution of technology will speed up and speed up and speed up until, and will eventually, at that point, 10 years from now, if we were at that point, we wouldn't even be able to recognize ourselves because we'd be so different, we'd be so modified by technology, right? And that point is essentially about where computers would be smarter than people, right? Because if they're smart enough to if we're smart enough to make computers smarter than us, then they'll be smart enough to make themselves smarter than they are, right? And then the vicious cycle, right? Where the technology is just exponentially, technology has been growing, growing, growing. His prediction is that it'll eventually do this, right? And essentially we'll be like one with the stars or whatever at that point,
There has to be some limiting factor.
Right. I'm not saying I subscribe to it, but I do feel that.
I do almost feel it happening in the culture.
Yeah, I think change is happening more quickly. And given, like what I've been talking about, given maybe one of the disturbing things I'd say about bias in machine learning is that this is not something that we just now found out about, right? Like, I mean, people knew this was going to be a problem, and it happened anyway. It's like watching a train wreck in slow motion or something, it's like what's going to happen, and you're just watching it happen, right? And I think when we talk about the rapid increase in, technology development, yeah, that's scary because, like, I don't know that it'll be a smooth ride. Like, I don't know that we're going to be super cyborgs or whatever, but I do feel that technology will increase more quickly. Like, it will, I believe that in his prediction, that it will more rapidly, increase. And yeah, obviously I'm about as far from a Luddite as you could get, but that does worry me.
Of course, this is a concern, of course.
Well, thanks for coming out.
Yeah, thank you.
And a round of applause.
Thanks again.